Okay, thanks, Giordano. Everyone, welcome to our OpenSim webinar. My name is Jennifer Hicks. I'm the OpenSim R&D Manager, and I'll be serving as the moderator for the webinar today. Giordano, can you mute your microphone just for now? I'm getting a little feedback. Okay, it's better now, so I'll keep going. So I'm pleased to welcome today's presenter, Giordano Valente. Giordano is a bioengineering graduate student at the University of Bologna in Italy, and he's going to give us an overview and a demo of the NMSBuilder software, which can create a subject-specific OpenSim model using imaging data. Can you go ahead and click through the next slide? So first, a little bit about OpenSim and the OpenSim project. OpenSim is freely available software for visualizing musculoskeletal structures and simulating movements of humans and animals and robots and more. The application includes tools for general purpose inverse dynamics, optimization to estimate muscle and joint forces. There are methods to create simulations from motion capture data, and then tools to analyze and visualize the results of your simulations and motions. So the first goal of our webinar series is to showcase cutting-edge research that's being performed with the OpenSim software. OpenSim is also a growing and geographically diverse community of users. So the second goal of our webinar series is to provide an easy platform for the OpenSim community to communicate and collaborate. Next slide, please. Just a couple reminders before we get started about the webinar format. We'll address questions at the end of the presentation using the Q&A panel. And if you need any additional technical help during the webinar, you can consult the guide on our website. The URL is listed there. So now let me introduce Giordano, and we'll get started with the great webinar and demo that he's planned for us today. So again, Giordano is a PhD candidate in the bioengineering department at the University of Bologna, and he's working on a project that's funded by the Rizzoli Orthopedic Institute. His core research interest is the development of subject-specific musculoskeletal models specifically of the lower limbs. And he's using these models to predict skeletal loads, and he's also analyzing the sensitivity of the parameters, a key validation step. So Giordano is a member of the NMS Builder project, funded by the European Union. And on this project, he's the application expert, providing a modeling perspective for developing the NMS Builder software. So today he's going to give us an overview and demo this software for personalized musculoskeletal modeling and simulation. So with that, please take it away, Giordano.
Okay, thank you, Jen, and thank you everyone for participating in this OpenSim webinar. So my name is Giordano Valente, and today I'm very pleased to be presenting the NMSBuilder software, which is developed within the NMS Vision project, funded by the European Union under the 7th Framework Program. So the webinar goals today are, first of all, to demonstrate the power of the NMSBuilder software, which represents a complete and unique framework for creating subject-specific OpenSim models of the musculoskeletal system. Then we want to give some insights into how the NMSBuilder software can be used to solve a specific research problem. I'm going to present a simple illustrative case study as application to a research question. And finally, we want to provide some additional information on software releases and how to communicate with us. In the past few years, an increasing attention has been focused on the relevance of subject-specific modeling of the musculoskeletal system, and in particular, the influence of specific musculoskeletal geometry was found on model prediction. So, for example, some significant differences were found using generic scale models and image-based models in calculating the muscle moment arms and musculotendon length. And when applying this to a dynamic simulation of human motion, it was found that skeletal geometry affects both muscle and so the joint contact forces during motion tasks. And also some errors were found in the calculation of the muscle potential acceleration using generic scale models compared to the subject-specific models. So if we pose this question, when a subject-specific model is needed, Of course, the answer is it depends on the research question. If we focus on the OpenSim software, considering it as a software tool for dynamic simulation of human and animal movement, we all should know that OpenSim has no preprocessing environment. And that means that if we want to build subject-specific models, we necessarily need to deal with the OpenSim model file format, so we have to work with it. And this is an XML format with a .osim extension. And this is on the right, it is a typical model file structure with which we necessarily need to deal. And it can take a lot of effort depending on the level of the subject-specific scenario. So when we go and set up subject-specific modeling framework, we need to take into account that we need necessarily some preprocessing skill expertise. And this means that we need to be able to edit and process imaging data. We need to have an important knowledge on multi-body dynamics modeling with the application on the musuloskeletal system. We need to know how to work with the OpenSim model file formats. And moreover, we need to have programming capabilities in order to build up these subject-specific models. And this means that we need to be able to program with MATLAB or C, C++, and so on. And this leads to conclude that in general, to set up a subject-specific framework is an expensive process in both time and effort. So with this scenario, NMS Builder is a very powerful tool to help speeding up this modeling framework. And in particular, if we consider these three phases, so a pre-processing phase, a solution phase, and a post-processing phase, the NMS Builder software can help speeding up this framework in both the phases between the creation of subject-specific models and the OpenSim simulation, so our dynamic solutions, and also in between the simulation in OpenSim and the post-processing phase in analyzing the model outputs to answer some specific research questions. So going into more detail, we want to see now what is needed to create a subject-specific model in OpenSim. This is a simple figure, so for a basic model. And since we have to deal with multi-body dynamics models, we need first of all to model our tissues as rigid bodies. And that means that we need to have the geometry of the bodies, first of all, and then to assume that such bodies are rigid, we need to calculate the inertial properties of the bodies in terms of mass, center of mass, and inertial tensor. Then, when we have defined those bodies, they need to be connected. So we need to define some ideal joints. And in OpenSim, that means that we need to define the location and the orientation of the joints in parent and child. We also need to define the kinematic constraint of the different model joints. And also, we need to model the muscular system because the muscles are the elements that allow to move our rigid bodies. So we need to model the muscle actuators in terms of muscle actuator paths and also some important muscle parameters that are needed to run dynamic simulations. So today, I'm going to present this case study, which is a simple illustrative problem. So we want to start from MRI scans of a full lower limb body of a normal volunteer subject. And our first aim is to generate a baseline model from anatomical surfaces that are segmented from this lower limb MRI. And so we want to build this musculoskeletal model of the lower limb using a ball and socket joint at the hip, so a typical spherical joint, and then with a hinge joint, so a 1 degree of freedom rotable joint at both the knee and the ankle. And then we want to modify this model, so we want to increase the patella of this subject. So I'm going to build two modified models. The first one that has a 1.3 time increased patella, and a second one with a patella increase of 1.5 times. And we want to see what happens to knee reaction forces during walking if this particular subject has a bigger patella. So now I'm going to, first of all, create this baseline model, following this, all these phases of the previous slides, and showing you how to do it with the NMS Builder. So the first step is going to be to obtain the geometries of the bodies, starting from the imaging data. And I'm going now to switch to the software. So this is the NMS Builder, how it looks like. And here I have imported from the DICOM format a set of MRI scans of the full lower limb MRI of this subject. And here on the right, you can see all these different data objects that in this software are called VME, which stands for Virtual Medical Entity. So it's basically the data object of each set of information. So here, for example, we have segmented this lower limb scans elsewhere, in particular using the software Amira. And here you can see all the surfaces that I will turn on in a second. But first of all, I want to show you how it is easy to import the surfaces segmented elsewhere. So for example, if I want to import a bone, I'm just going to import geometries STL, because I'm going to import, for example, let's say a tibia in an STL format. It's going to be shown here in the data tree panel. I'm going to turn it on, and this is the tibia segmented elsewhere and easily imported in the software. And so on for all the other lower limb elements. So for example, I'm going to turn on the different surfaces of the thigh and the shank and the pelvis and so on. And those VMEs are registered onto the specific MRI scans of the subject. And you can soon note that, of course, we have differentiated between the different tissues of the system. So you can see the external surfaces representing the soft tissues, and you can see the hard tissues representing the surfaces of the bones. So going back to the slides, here we have obtained the geometries of the bodies. Now we want to assume that such bodies are rigid because we want to deal with a multi-body dynamics model. So we need to, in order to build up this baseline model, we need to define the inertial properties of this system. So here, for example, let's focus on this particular part of the model. So you see the pelvis part and the thigh part, and they are made of external surfaces, so the soft tissues, and then hard tissues. So in order to calculate the inertial properties, first of all, we need to define the density of each tissue. So if I focus, for example, on the external surface of the thigh, I will use a feature which is called VME metadata, which allows to store some attributes for a particular VME defined here in the data tree. So I'm going to pick VME metadata, and here I can define for a new tag. So I want, for example, define a particular density for this tissue. So I'm going to create a new tag, select it, give him a name, which is density in this case, and then type in the numerical value. That could be, for this case, a typical value could be 10 to the minus 6 kilogram over meter cube, so like this. And then just pick OK, and these parameters are now an attribute of this particular element. And so on for all the other bodies which are present in the model. Once I have done this for all the elements, for example, let's again focus on the right thigh, I am ready to calculate the inertial properties. And this particular feature can take into account the multi-surface body. So, for example, here I have defined different density for the hard and soft tissue, and now I'm going to calculate the global inertial properties of this particular multi-surface body. So, operation, measure, compute inertial tensor, and here I'm ready. I just had to pick OK. I'm not going to do it for time limitation because it's going to take some minutes. So if the user assigned density, it will take into account this. Otherwise, if the user does not set the density, a default density will be taken for this particular calculation. What I'm going to show is the result, because when I measure, I calculate the inertial properties, automatically they will be attributed as VME metadata. So if I pick right thigh, I go into operation, modify, VME metadata, you will see all the calculated inertial parameters. So here you can see the surface mass, and it's 8 kilos and something. And then you see here all the different components of the principal inertial tensor, and also the inertial tensor components of the inertial matrix calculated with respect to the local reference frame of that particular body, which is the most important thing, because those elements will be passed to the OpenSim model. So here, for example, just to show you, I can visualize all the different components of the matrix, 2, 3, and so on. So in that way, I'm done. So again, imagine to extend this to the full lower limb model. And here I'm done with the rigid bodies part. I am now ready to go and define the elements necessary to connect such body. So I'm going to define the joints necessary to create this baseline model. And here, I'm going to show you, for example, let me again focus on the thigh body. I'm going to create the hip reference frame, because you know that in OpenSim you need to define the location and orientation in parent and in child. So let's focus, for example, on the hip joint. And let's say I want to create the hip reference frame in child, so with respect to the thigh body, according to the ISB standards, for example. That's what I did for my model. So here I need, first of all, to palpate some relevant anatomical landmark, and this is possible to be made by hand, so picking the landmark in the appropriate position, or registering some atlases into this specific anatomy. So once I have this marker palpated, I go and create a reference system, and the most general way to do it is using this feature. So operation create new reference system. And yeah, it's going to be here. So I'm going to increase the scale first of all, and you'll see this reference system placed in correspondence of the global reference frame of our system. So I'm going to define this reference system selecting a plane. So according to the ISB standards, I need to pick, first of all, the origin, which is the midpoint between the lateral and medial epicondyles of the femur. Then the second point, defining the first axis, will be the hip joint center, which is the center of the femoral head located here. And then the second point is going to be the lateral epicondyle of the femur, which is this one. And here we go. This is the reference frame in the body reference frame placed here in the right center. So now I just need to center this reference frame here in the hip joint center, and this is going to be the hip reference frame in child. So since this is a particular VME which is called static, so it is not dependent on other VMEs, before moving this particular VME, I need to freeze it. The operation is called freeze. So I'm going to operation, create, derive, freeze VME, and it just created a copy of this particular VME, which is now I'm able now to move this particular reference frame. So I'm going to operation, modify, move, and the move panel, yeah, will show up now. And I want to place this in correspondence of the hip joint center. So I'm going to pick an auxiliary reference system from the data tree, which is the hip center. And now I just need to put the XYZ values into 0. And here we go. This is the joint reference frame, the hip joint reference frame in child. So with respect to the thigh. So if we extend this to all other joints that we want to model, so 2 hip joints, 2 knee joints, and 2 ankle joints, with the same exact procedure, we are done. And the other part that we need to, the other part that we need to define to create the joints are the definition of the kinematic constraint. So I want to create a ball and socket joint or a hinge joint, but I don't need to do it now because this will automatically be handled in the procedure of creating the OpenSim model that I will show you later, because the user has just to choose the type of joint later on. So I'm now ready to go to define the muscle actuators in terms of actuator path. So I need to define the origin, the insertion, and the different via points eventually. And I also need to define the muscle parameters of each actuators. So switching back to the builder, let's focus on this model subparts, so femur and tibia. Here you can also see some markers which represent some origin via an insertion point of some muscle. And let's say that I want to define, for example, a vastus lateralis muscle actuators. I have all the data necessary, which are necessary to do this. So I know where is the origin, the insertion, and the via points of the muscle. So I go and derive the so-called rapid action line. Operation, create, derive, rapid action line. Here we go. I can change the name of this. So in the VME tab, I'm going to call this vastus lateralis. I'm going to pick the manual method to define this, and I need to pick the starting point of the actuator, which is the P1, the point 1. I'm going to pick the ending point, which is going to be the insertion point on the patella. It's this one. I can also define some midpoints, so the via points of the actuator. And in this case, I just have one via point for this muscle. It's going to be this point 2. Here we go. You see the actuator path of the vastus lateralis. I can play a little bit with the visual properties. So, for example, I don't want to see the label, so the measure of the distance between the origin and insertion point. So I'm going to take it out. I want to visualize this as a tube and not as a line, for example, with the radius of, let's say, 5 millimeters. And this is the actuator part. And then, using the same feature that I've shown you before, so the VME metadata attribute of this particular VME, I can go and define the muscle parameter of this element. So, operation, modify, VME metadata, and here I can define the valid muscle parameters which are defined, which need to be defined in OpenSim. So, for example, I want to define the maximum isometric force of this muscle, and I'm going to add a new tag. I'm going to call it max isometric force, and I'm going to type in manually the numerical value of this force, which can be, for example, 1800 Newton. And that's it. I'm done. So this is the definition of the vastus lateralis muscle actuator. So imagine to, again, extend this procedure to all the muscles that you want to model. And in this case, I have registered the belt model, so I have 86 actuators with the appropriate properties derived from the subject-specific data. And now I am ready to build up the OpenSim model. So again, let me focus on a model subpart. So let's say that we have the thigh and the shank. We have defined everything that we need. So we have modeled the rigid bodies. We have defined the joint. We have defined the muscle actuators. So here we have the thigh, the shank, with the different inertial properties taken into account, hard and soft tissue. We have defined the the joint reference frame, in this case the knee reference frame in parent and in child. We have defined the properties of the muscle actuators. I am now ready to build this sub-model. So I just have to go into Operation, Create, New, OpenSim Model from Wizard. And this is a step-by-step guided procedure, which basically will create the C++ source code that is going to use the OpenSim API to define how the OpenSim model will be created. So let's start. I'm going to create multi-surface bodies. So I'm going to pick the two multi-surface bodies that I want to model. So right thigh and right shank. And this will take into account all the other surface with different inertial properties. Click OK. Bodies added to model. I can go ahead and define the joint. First of all, it is mandatory in OpenSim to define a free joint between one body and the ground. So I'm going to pick here free joint with the ground, and my child body is going to be the right thigh. Click OK, add joint, done. And then I'm going to define a pin joint, so a 1 degree of freedom rotary joint between the thigh and the shank. And here I need to define my parent body, which is the right thigh. My reference system in parent, which here it's called right knee in parent, which is the reference, the joint reference system in parent. And as well, I need to define the child body, which is the right shank, and the corresponding reference system, which is here called right knee in child. Add joint, and the pin joint is added to the model. Going forward, I can add some source landmark cloud to be added to the corresponding target bodies. So, for example, I want to add this landmark cloud to the thigh. Pick this, OK, my target body is going to be the right thigh. Add marker set, OK, and as well, I want to add this other landmark cloud to the shank. So I pick this cloud and selected the right shank, add marker set, done. Last step of this wizard procedure is to add the muscle actuators. In this case, I just have to pick, let's say that we just want to include the vastus lateralis muscles. I just have to pick what I had defined before, so the rapid action line with the corresponding properties of the vastus lateralis muscles. OK, and I'm done. So now the wizard has finished, and the source code will be added to the data tree. You can see it here, and automatically this window pop up showing the C++ source code that uses the OpenSim API to generate the .oc model. So if I'm happy, so if I don't want to modify anything, I'm ready to compile this, so to create the real OpenSim model. So I pick it on the data tree, I go into Operation, Modify, OpenSim Model, Editing Tool, and I just need to pick the Generate Model, so the source code will be now compiled, and the OSIM model will be created and automatically show up in this window. Here we go. This is the output model in the OSIM extension, which is ready to be imported in OpenSim. And I'm going to do it now to show you the result. So I'm in OpenSim 3.0. I'm going to select File, Open Model. This is the default directory where all the NMSBuilder parts are stored. So this is my output model that I just created right now. And here it is. This is exactly the model subpart that I just created. So here, if I go and navigate all the elements, you see all the different bodies. So for example, under right eye, I can display geometries. I'm going to decrease a little bit the opacity to let you see, yeah. So the other tissue and the muscle actuators that I've defined. You can move the body, so see the generalized coordinates and see that I have properly defined the knee joint. So yeah, imagine to extend this procedure to our full musculoskeletal model. So I go back into OpenSim and I will show you the result. So exactly doing what I just did, but for the whole lower limb system. I'm going to open, find it. My baseline model. Yeah, here it is. So this is our model with 86 muscle actuator with the specific muscle properties, with a ball and socket at the hip and a hinge joint at both the knee and the ankle. Now going back to our research question, so after we have defined this baseline model, we want to see what is going to happen if I change dimension of the right patella. So what's going to happen in the dynamic simulation results if this particular subject had a bigger patella. And this is something very easy to be done in the NMS Builder, because, okay, here you can see the baseline model with the normal patella and the 4 insertion points of the quadricep muscle, so the 3 lati and the rectus femoris. So here I can scale this data set easily. So I pick the patella, I go into Operation, Modify, Transform, and I want, for example, do it with a gizmo. So I'm going to select gizmo. I'm going to tell it that I want to scale this data set with respect to this reference frame, which is centered in the centroid of the patella. So I'm going to choose as auxiliary reference system this one. And here, if you see the scale XYZ factors, you will see that if I play with this, the patella can be easily increased or decreased. So what I did is to perform this operation using the factors 1.3 and 1.4. So I scale this linearly along the 3 directions, and the result is this. So this is the 1.3 times increased patella with the corresponding markers of of the insertion points of the quadriceps. And this is the 1.5 times increased patella. Of course, you can understand that now what I need to do is just to rebuild the OpenSim models with this modification that I just did on the patella, and I'm done. And the alternative is, to do this, I have two alternatives basically. Rerun the wizard procedure, or for more advanced users, just go into the C++ source code and modify just the part of the patella. I'm not going to do this for time limitations, and I'm just going to import the result in OpenSim. So open model, this is the 1.3 model. So you see here the patella increased with the of 1.3 times, and corresponding modification on the insertion point of the quadriceps. As well, I can do it for the other model, so the even bigger patella, so 1 times increased patella. Here we go. Those are the three models of interest that I wanted to create. So what did I do with such models? Going back to our research question, we want to see what happens if this subject had a bigger patella. So going back to the slide, what I did is to perform several simulations using those three different models. First of all, I performed inverse kinematic simulation of normal walking to calculate the joint angles during gait. And this is possible to be done either in NMSBuilder or OpenSim, because NMSBuilder can leverage OpenSim to perform some simulations. In particular, we have implemented the inverse kinematics, inverse dynamics, and static optimization. I'm not going to demo this because of time limitation. And then we went and performed a muscle analysis in OpenSim to calculate the moment arms of the quadricep muscles, so of the 4 muscle actuators. Then we went into static optimization, performable in either NMSBuilder or OpenSim, to calculate the muscle forces. And finally, in OpenSim, we performed a joint reaction analysis to see what happened to the knee contact forces during walking with those modified models. Oops. And let's go into some results. So first of all the quadricep muscle moment arms increased, and this is pretty obvious because when the patella increased, you can imagine how the moment arms increased. But let's go and see what happened to the knee reaction forces. Here I have plotted the 3 components of the forces, so Fx, Fc, and Fy, during the spent phase of the simulation. And for example, if we focus on the first peak, you see that the bigger the patella and the lower are the knee loads. On the second peak, on the other way, essentially the knee reaction forces did not vary. Why this happened? Let's go and see the muscle forces. If we focus on the best eye forces on the first figure, we see that such forces mostly determine the first peak of joint reaction, of knee reaction forces. And you see that the bigger the patella, the lower are the best eye muscle forces. And so this went and determined the increase of the first peak knee reaction forces. On the other hand, if you go and analyze the second peak of knee reaction forces that basically did not vary, you see that what mostly determined the second peak force are the rectus femoris and the gastrocnemius forces. And you see that the bigger the patella and the lower are the rectus femoris forces, as well as the best eye forces. But on the other hand, you see the gastrocnemius force, which is slightly increasing to compensate for knee extension force. And this led to have to not let vary the second knee reaction force peak. So basically, this simple elucidative study led us to conclude that, recalling the first question that I posed some minutes ago, when a subject-specific model is needed, depends on the research question. In this case, with this simple study, we demonstrated the need for subject-specific models because we created this baseline model with specific MRI scans, and we went and modified the dimension of the particular body according to the specific anatomy of the subject. And most important conclusion is that this can be done with the NMS Builder, which is a valuable tool for subject-specific modeling of the musculoskeletal system, and can help a lot saving both time and effort to set up this subject-specific modeling frameworks. So I want to spend a couple of minutes now to go in some more detail into what NMS Builder is, and to provide some additional information on releases and communication. So basically, as I told you before, it is a software package developed within the NMS Fusion project, which will end next June 2013. And the main aim of this project is to integrate, well, from the software point of view, is to integrate the MAP2 application, which stands for Multimode Application Framework, which is basically a framework for computer-aided medicine application, and the OpenSim software. And this integration is made for create subject-specific models from specific clinical data, basically to have different features for import and edit a lot of different biomedical data coming from different sources, to be able to visualize and fuse such data, to then be able, as I've just shown you, to build full-scale personalized musculoskeletal model, and be able to create and export such models in the OpenSim model file formats, and then to leverage OpenSim to run OpenSim simulation and store back into NMS Builder the results performed in OpenSim. So, as you may know, we have released a first alpha version of the software with some additional material. So, if you go into the dedicated Biometan page, you will find a package installer with all the necessary additional software. We have distributed a user manual together with some test data, which are basically a part of the data that you just seen in this webinar. And also, we have distributed a getting started tutorial, a paper-based getting started tutorial to get familiar with the test data distributed with the first release. Also, we have just launched a user forum on Biometan, so feel free to post questions and comments related to any topic on the use of the NMS Builder. And of course, also feel free to contact us if you have additional questions, requests, and anything. And those are our emails of the development team of the NMS Builder. And I also want to add something on installation of the software. As you've seen in the webinar, the Builder now supports the latest OpenSim version, which is the 3.0. And we have released just this morning, actually, another version of the NMS Builder, which integrates the 3.0 version. And this version is still under testing, so maybe you can find some bug or some problems. You know, it's an open version. So, as well, feel free to contact us and report any bugs or anything related. when you go and install the software, everything is automatically handled by the installer. And you have to know that, of course, some prerequisites are needed for this version. First of all, obviously, you need to have installed in your computer the 3.0 version of the OpenSim, but you also need to be installed the Visual Studio Express and the CMake that allow to compile the OpenSim model. Finally, some additional information of the project development. So we are now refining the integration with OpenSim 3.0, and also we are working on additional visualization features and also on a statistical post-processing of the simulation results that can be stored in the VME elements of the model. Also, we are working on a kind of integration with MATLAB. So it's going to be possible soon to have MATLAB file format exchange in terms of import-export facilities. And also, we are thinking about software customization for a typical research question that some user groups might have. And with this, I concluded my my demo. First of all, I want to thank you for your kind attention, and also I would like to thank the NMS Vision project, as well as my lab here in Italy, the Medical Technology Laboratory in the Ruzzoli Institute, and also, of course, the OpenSim team in Stanford for their very kind support.
All right, thanks, Giordano. That was a great talk and a great demo. Let's go ahead and get started with the Q&A session. Can you advance to the next slide for me, Giordano?
Yes, sorry.
Okay, so if you have, please ask questions. All of these questions will be text-based, so go to the Q&A box and at the bottom right of your screen, and then type in your question. Make sure you select to ask all panelists. Giordano, can you mute your speaker? It's getting some feedback there. So with that, let's go ahead and open up the questions. So we already have one question from John DeWitt. So how is creating this subject-specific model different than scaling a generic model?
Oh, sorry. Could you say it again?
How is the process of creating the subject-specific model different from the, say, the scaling using the scaling tool in OpenSim that scales a generic model?
Yeah, of course, it is a completely different process because first of all, you need to have segmented surfaces of the anatomy of a specific subject. So you need to have accurate surfaces of both hard and soft tissue, and then the process it's not actually very time-consuming, but our framework includes, as you've seen before, to import all the necessary surface anatomies, and then go and proceed into the anatomical landmarks virtual palpation, and then to go and define all the different model components necessary to build a multi-body dynamics model. So I can say that of course it is more time expensive than scale a generic scale model, a generic model. But with this tool, we cannot complain actually, because with a 2 days you can have a full-scale lower limb musculoskeletal model.
Okay. Now I have another question. Rob Siston has a question about more details about building the model. Can you provide some more information about how you calculate the moment arms for the model? Are you measuring distances based on the image data, or using the excursion method, or some combination of those two?
Well, basically, if you mean how to calculate the muscle moment arms in this study that I've shown, this is just a muscle analysis performed in OpenSim, because so far we have not implemented in the software a feature that allows to calculate the muscle moment arms here. We are planning on this.
The muscle moment arms just come from the way that the imaging data is combined to set the muscle paths and the bone geometry.
Yeah.
Okay, so this is my follow-up question. So then when you're developing your own subject-specific model for some research purpose, do you do a testing?
Oh, so you mean how to define the actuator paths? How do we place the markers defining the actuator path?
No. So do you do any sort of validation step where you compare the muscle moment arms that you get from the image-based model to?
Oh, yeah, exactly. We did that. So basically, for this particular muscular model, we imported basically the origin via an insertion point of the depth model, and we registered such anatomical landmarks onto this specific anatomy, and then we superimposed all the actuator paths onto the MRI scans of the muscles to have a visual check of the accuracy of the actuator path.
Okay, I see. So then are you getting the other muscle tendon parameters from that model as well?
Good question. So for this simulation, since we have just run a static optimization excluding the force length velocity properties, we just needed to have set the maximum isometric force of the muscles. But if we wanted to do different simulations, so including the muscles physiology, we would have relied on on some algorithms developed in the literature to go and calculate some other muscle parameters that cannot be derived from the clinical data,
Okay.
So we rely on the subject-specific data only when we can, basically. So the maximum isometric force, of course, we do rely because we go and measure the physiological cross-sectional area, and then from that, we derive the maximum force. From other parameters, but this is not the case so far, maybe we cannot rely on the clinical data, but we need to basically scale based on some algorithms developed in the literature.
Okay, thanks for explaining that. It's an important point. So now we have another question from one of the webinar listeners. This is Liang Ching Sai. Apologies if I mispronounced that. The question is, what kind of MR images are needed for NMS Builder? Is there any specific MR scanning sequence?
No, you don't need any specific MRI scans. You just need to have them, of course, in the DICOM format. So if you mean, for example, the sequence of the images or other MRI parameters, it doesn't matter at all. You just need to have a DICOM format and you're ready to import and edit the images.
Okay, now a question from Luca Modenisi. How long does the process take of creating a subject-specific model from imaging data?
Well, basically, mostly it depends on the segmentation time, because otherwise, now that we have this modeling framework well consolidated, it really takes, with an expert modeler, really few hours or some days, no more. It depends mostly on the segmentation time, actually.
Okay.
So I can say that now, compared to other modeling framework that we use here in our lab, it's very fast, because with few days we have a full-scale lower limb model.
Okay. how, so say you only have partial imaging data, would you be able to combine that with, say, a scaled generic OpenSim model?
Yeah, and actually we are already thinking about this because we got some requests from some modelers that wanted to actually do a kind of this procedure. So of course here you can import any geometry. So for example, let's say you want to import the depth model distributed with the OpenSim software. So you can combine both subject-specific data and generic data coming, for example, from the depth model, and fuse them, edit them, and of course combining according to the to a particular application, of course.
Okay, thanks. Now a question from famous Tumanadu. What is the process of getting muscle tendon length changes of the muscles over the time history of gait? How would you do that with a subject-specific model from NMS Builder?
I think you mean how did I calculate the musculotendon length in a mice simulation? This is something related exclusively in OpenSim, because the simulation that I performed, the muscle analysis that I performed, it's just using the OpenSim tool. So it's not related to NMS Builder, that it's a tool of OpenSim. So
then you would create the subject-specific model in an NMS Builder, import it in OpenSim, and then do a muscle analysis.
If you mean this part, so how I went and calculate the moment arms and the musculotendon length, it's everything related into the muscle analysis in OpenSim. But also, for example, if you mean this, but also you can calculate the total muscle tendon length that you define here in the muscle actuator, just defining the actuator himself, because here I can just turn on the label and you see the length of the whole muscle tendon actuator.
Oh, okay, I see. So let's move on to another question. This is a good one from Andrea Morelli. Have you compared the kinematics results or dynamics results for a scaled model in OpenSim, so using the scale tool, to a customized model built using NMS Builder?
Yeah, actually, of course we did it. Basically, I cannot say much about this because it's a project of our lab. But yeah, we did compare the results of scaling a generic model onto this anthropometry of the subject and using this subject-specific model. Basically, what I can say now is that when you deal with normal subject, the differences in terms of kinematics and dynamic results can be considered negligible, at least for walking trials.
Okay, so that gets back to your question or your point about needing a subject-specific model depends on your research problem. So then did you also look at pathological patients as well, people with bone deformities, or have you just compared typically developing people?
Yeah, with this workflow, we just have compared it with normal people. But in the past, a couple of years ago, we performed a study on a pathological subject who underwent it's a case of pediatric oncology, and it's also published in Clinical Biomechanics. And we used this very similar modeling framework without having the NMS Builder But yeah, going back to the question, we did not compare this with, we did not apply this framework to pathological subjects so far.
Okay. Now, Julie Thompson has a question that's following up on our earlier discussion about muscle tendon parameters. So she's wondering, since you didn't calculate the force length velocity curve, is that why you use static optimization instead of CMC?
Exactly, exactly.
And so how difficult would it be to get a model that's suitable for CMC from the NMS Builder?
Well, we need to know the muscle parameters, because as I said before, if you can derive the muscle parameters from the specific MRI images, you know them. Otherwise, you need to derive them from the literature. Well, adapt them from the literature. So as far as you know the specific parameter, you can input them to the model and use it for a particular simulation. Actually, another okay, this is an illustrative problem. So we have just decided to go for static optimization, excluding the muscle physiology. But basically, what we expect is that in this case, so for the normal subject, for a walking trial, if you go for CMC or static optimization, the results will not change a lot. That's what we expect.
Okay, I think we've gotten to most of the key questions from the audience. I'll ask one final closing question. So if people want to get started using NMS Builder, you said that there were tutorials. Can you tell us a little bit about what those tutorials teach? Yeah,
so basically in this slide, to summarize what we have distributed so far. So first of all, I suggest to, of course, download the package installer, and you can already find the version integrated with the 3.0 OpenSim version. Download the user manual together with the test data and the Getting Started tutorial. And start playing with the software, of course, accordingly to your research problems, of course.
And then, Giordano, what's the content of those tutorials? What will they teach people?
The tutorial will explain how to build a musculoskeletal model for OpenSim using the test data that we have distributed with the application. So basically, it's a two-body model, including the thigh and the shank bodies, with all the necessary elements. And the tutorial will guide the user to build up an OpenSim model starting from this particular distributed test data.
Okay, great.
And of course, do not hesitate to write on the forum or contact us if you have additional questions, problems, comments.
Yes, so Giordano's email is up on the slide now. So if we didn't have a chance to get to any of your questions, please feel free to contact Giordano or go on their user forum and ask those questions.
Yes.
Can you bring up our final closing slides for me, Giordano? Okay. So thank you all for a great discussion. Just pointing out some of the OpenSim project sponsors. So OpenSim and this webinar series are supported by several grants from the NIH and the European Union. This includes an NIH grant that funds our National Center for Stimulation and Rehabilitation Research. Next slide, please. So if you want to get more information about OpenSim, the National Center for Simulation and Research Rehab, upcoming events, other resources, please go to our website. You'll also, when you exit the event, you'll see a survey that will appear in a pop-up window. Please fill out the survey to help us improve the webinars and choose upcoming topics. So again, thank you all for participating. Thank you for all of the great questions. and we hope you'll continue to tune into our webinar series and stay involved with the OpenSim project. And also go and download and check out NMS Builder. Thanks.
Thank you.